Hi, I'm Ben Leatham, and I'm going to present work done by the adaptive experimentation team at Meta, in which we use Bayesian optimization to combine offline and online experiments for policy search and online ranking systems. Ranking systems are an important part of many internet services, and they generally consist of a few components that all work together to produce a ranked list of relevant items. AutoML is important for every component of this system. We can use AutoML for source selection of the retrieval system. We can do hyperparameter optimization of the learning algorithm. And AutoML can be used to learn an effective ranking policy, which is often called the value model. Evaluating a ranking system requires running an online test, which is generally time-consuming and can often take days or even weeks. Sample efficiency is thus critical for applying AutoML to ranking systems, and so Bayesian optimization is a popular approach. For instance, the value model, which is a ranking policy, has various parameters for combining interaction predictions, like the probability of a like or a comment, with other attributes of an item, like whether or not it's from a close friend. These parameters, here shown as alphas, can be learned with BayesOpt through online experiments. Here's a quote from the machine learning team at Instagram about how BayesOpt is effective at improving ranking policies. Because online experiments are so time-consuming, offline simulation is a very appealing alternative. We can do offline simulation by replaying queries to the modified system we want to evaluate, generating a new ranked list, and then simulating the user interactions that we care about with that ranked list. This is easier said than done. The way that humans interact with the ranked list is complex and difficult to accurately simulate, in part because of feedback loops and interaction with content and with other individuals. We've seen several approaches at Meta to offline simulation, some using real-time data, others doing off-policy evaluation, but we have yet to see a case where these simulators are generally well calibrated. Rather, the offline estimates are generally quite biased. This video shows the results of evaluating 20 different configurations of a Facebook ranking system, both with an online test and with an offline replay simulation. Each panel shows a different outcome of interest, and each dot is a result for a particular set of parameters. While the offline results are generally correlated with online results, there's a very clear bias. This bias means that we cannot tune the system totally offline, since we don't know how a particular configuration will balance the online outcomes that we care about. In this work, we study the use of multitask Bayesian optimization to combine offline and online observations for automated tuning of ranking systems, the goal being to reduce the number of online observations required. Some of the particular questions we study are, what are the underlying assumptions, and are these held in online ranking systems? Does it work? And if so, why does it work? We'll talk about each of these briefly now. The underlying assumptions depend on the kernel. The primary kernel used in multitask BayesOpt is the ICM kernel, the intrinsic co-regionalization model. This kernel separates the covariance into an intertask covariance matrix, B, that models the relationships between the tasks, and a spatial covariance function, kappa, that is the usual Gaussian process model of covariance across the parameter space. A key assumption made here is that the tasks have the same spatial kernel. For instance, if using an ARD spatial kernel, we assume that the length scales for each parameter are the same for each task. The ICM kernel implicitly models each task as a linear combination of latent independent GPs. Thus, the simulator bias, which is a difference between the tasks, must also be a GP with the same spatial kernel. Ensuring smoothness of the bias is thus an important consideration when designing offline replay systems. These assumptions generally hold in the Facebook ranking system we are considering here. We can use model cross-validation to evaluate the usefulness of any particular model. And we do so here on a real ranking system tuning in which we are tuning 10 parameters and have made 20 observations using online evaluation. If we try to do regular Bayes-op tuning by fitting a single task Gaussian process, the model fit is quite poor, as can be seen in the cross-validation plot on the left. 20 observations is simply not enough to predict in 10 dimensions in this problem. If we take those same 20 online observations and we augment them with 100 biased offline data and combine them with a multitask model, we get excellent model predictions on the online task. The good model predictions lead to good optimization performance, as we show in the paper. So why does multitask Bayes-op work in this setting? The GP prediction at a point is a kernel-weighted average of its neighbors' values. As such, there are generally two ways that offline evaluations can improve the model predictions: by providing more and closer neighbors to the point of interest, and by improving the estimation of the kernel. We study both of these avenues of improvement in the specific context of ranking system AutoML. For the first, we study theoretical generalization results and show how empirical learning curves compare to their theoretical bounds. For the second, we show that in this particular setting, most of the benefit of multitask modeling is coming from improved kernel estimation. In the previous figure showing the improvement in cross-validation, it was not having 100 mirror neighbors that improved the model predictions. It was the improved kernel estimation of having 100 additional data points. In summary, the results in the paper show that multitask Bayes-op can be a highly effective approach for incorporating biased offline estimates into AutoML of real-world ranking systems. We show that the conditions in which multitask models perform well actually exist in the real world. And the important result is that we can get great benefit from offline simulations without requiring perfect calibration. That opens the door to using offline evaluation in a broad space of AutoML applications where full fidelity simulation is impractical or even impossible, ranking systems being one of them. For more details, please read the paper, and we've also open source software as part of the ATS package. I also want to mention that a recent paper from our group, currently on arXiv, provides a simulator for a ranking sourcing system, which we hope will be helpful for others interested in developing methods for this problem space.